So let's look at how a result like this could fail. And it's going to take you on the very start of a story. It's a very, very cool story that I have other videos about that I'll link right here. Um, so how could this fail? Okay, so what we're going to do is we're going to generalize just what we mean by an integer in a kind of a funky way. I'll call it a weird integer in this video. It's not an official name. I'll even call it a winteger. Um, and it's going to be a special kind of complex number. Now, an integer can be thought of as just a very, very special kind of complex number. If you think of the complex plane, it's just these dots equally spaced along the real line. Well, there's another way you could say spread out a bunch of dots in a somewhat regular way in the complex plane, and that is to take an integer a, has to be an integer, plus an integer b, times the square root of minus 5. Why that? I'll explain that in a second. Okay, or in other words, a plus b times I times root 5. Okay, so a and b are supposed to be integers. So it's definitely not any arbitrary complex number. They're very, very special. They're kind of scattered around in a grid pattern around the complex plane. And why would you do this? Okay, so there's various reasons why you'd consider things like this, but here's the simplest motivation that I know of. I want to answer a question that doesn't talk about weird integers or complex numbers or anything at all. It takes an ordinary integer, so let's say it's fairly big, maybe, to make it a little challenging, and asks the question, can it be expressed as the sum of a perfect square plus 5 times another perfect square? It's a great thing to stop the video and just experiment with that question, and start with small n if you're going to do it by hand, and just see which numbers can be expressed this way and which can't. Can you do like the first, I don't know, 30 numbers and answer yes or no and see what the pattern is, and then predict what's going to happen if n is a 20-digit number or a 100-digit number? I'll tell you what, I'll give you a hint. It's hard. It's not easy. For other questions like, is it the difference of squares or sum of squares, you'd probably be able to guess the pattern. This one, it's harder. Okay? And here's why you'd be motivated to introduce these guys. Basic bit of algebra. This expression factors if you allow yourself to introduce the square root of minus 5. A squared plus 5b squared is just a difference of squares if you take a plus the root of minus 5b times a minus the root of minus 5b. When these come together, you get a difference of squares, and so you get a minus square root of minus 5 squared. So the square roots cancel, the minus cancel, and you get this guy. Okay. So all I want you to believe for this is that problems like this that are really natural, and you can play with and get some experimental results without knowing anything, even about complex numbers or square roots, for God's sake, motivate you to introduce quantities like this. Integer plus root minus 5 times another integer. And so that's what we're going to call a winteger from now on in this video. Okay. I'll tell you again, much more to it. If you see my videos, why minus 163 is a cool number. 7 videos, maybe something like that. I go much more into this story, but not at a super advanced level at all. Okay. So to some extent, integers behave like ordinary integers. Okay. You can take like 2 plus root minus 5 times 3 and add it to 7 plus root minus 5 times 12. Okay, and get something of the same form. You can add 2 integers and get a integer. You can subtract a integer from a integer and get a integer. And the usual rules apply. You can multiply 2 of them and get something of the same form. It's not as obvious, but if you work it out and have even a little bit of familiarity with complex numbers, it totally works. Okay, but can we divide them? Okay, well, what do we expect? If these are generalizations of integers, we don't expect to be able to divide one integer by another non-zero integer exactly. That's not what we get even with integers. We can't divide in general without remainder. That's what the division theorem is talking about. Okay, what does the division theorem say? Okay, and this is where we want to go back to the original division theorem and think about what it really means. It says we can divide with remainder, and it controls what kind of remainder we have to accept. In particular, you can make sure that that remainder is small in a precise way. Okay, so let's go back to that theorem, and this is something that the book does a pretty good job of getting you into about what's subtle about the division theorem, even for integers. It says you can take an integer w, you can try to divide it by q, and you will fail most of the time, but the remainder that you get can be chosen to be smaller than the divisor. Okay, so why is that so important? Well, if you didn't have that last proviso, this would be a stupid and trivial trivial statement, okay? In the ordinary case, if I just said, given W and Z, I can express W as QZ plus R, that's really easy. Just pick any quotient that you could imagine. Just let it be an arbitrary integer, and then just let R be W minus QZ. That's just the same equation. Okay, so it's really crucial. The meat of the division theorem is in the statement that the remainder can be made small in a precise sense. And everything that we'll do after this that relies on the division theorem really relies on that statement. Okay, so in the next video, I'll talk about what the notion of small would be for a winteger. Another thing, I'm going to just have you take on faith that it's the right notion of small, um, and then show you that we get some interesting problems with that make it, I hope, clear that this division theorem can start to get dicey pretty quickly if you start generalizing.